The purpose of this lesson is for us to analyze a function's behavior by looking and seeing where the function is increasing or decreasing. And the second objective that we have is to be able to apply the first derivative test to find where we have any relative extrema. We begin by talking about what it means for a function to be increasing and decreasing. Here we have the formal definitions of increasing and decreasing, which say that if a function is increasing, and if we have two x values, one that's smaller than the other, then the y values of those functions follow that same order. So as we move to the right, the function is going up. So on this highlighted portion of the graph, that function is increasing. On the flip side, we have the definition for what it means for a function to be decreasing. If you have two x values that are getting larger, the y values are getting smaller. And we're always moving from right to left as we determine intervals of increasing and decreasing. In the piece here, you see we have a constant part of the function where the graph is not increasing nor is it decreasing. So that's just a recap from pre-calculus. What's going to be new for us, how we're going to be able to determine where these happen without looking at the graph even, is by using the derivative. Theorem 3.5 tells us how we can test for increasing and decreasing functions. Wherever the function is increasing, the derivative is positive. And remember, what that means is that the tangent line would have a positive slope. So if you notice on that increasing part, I draw in a tangent line, and that line definitely does have a positive slope. But if I were to draw in a tangent line on the decreasing part, that line would have a negative slope. When the graph is decreasing, the first derivative is negative. And of course, if the graph is constant, meaning that there is a horizontal tangent line, and horizontal lines have a slope of 0. So the derivative would be equal to 0. Next, we have guidelines on how we can use Theorem 3.5 in order to determine where a function is increasing or decreasing, and we will go through these guidelines with example 1. We begin by finding the critical numbers of this function. To find the critical numbers of this function, we have to take the derivative. Now that we have the derivative, we can go further and find critical values by looking for the places where the derivative is equal to 0 or the derivative does not exist. In this case, our derivative is a polynomial, and so it never happens that this derivative does not exist. But we can find places where it is equal to 0. I'll take f prime, set it equal to 0. I'll factor out the GCF, and then I'll set both of my factors equal to 0. This gives us two critical values of 0 and positive 1. Now, these critical numbers are supposed to be used to create test intervals. So we have to pay attention to which is larger than the other. We get 0 and 1 on the number line, and it creates three separate intervals. It creates an interval from negative infinity to 0. The second interval it creates in the middle is from 0 to 1. And the final interval it creates on the right-hand side is from 1 to positive infinity. Now remember that we know that f prime of 0 is 0, and we also know that f prime of 1 is 0. We know the value of the derivative at those two numbers. Those were the critical values. Now we're going to find the value of the derivative in each of these three intervals. So in each interval, we are going to choose a test value, a number that is, that falls into that interval. It doesn't matter which number you pick. So for instance, when I'm choosing a number in the first interval, I could choose -1, or I could choose -2. I could choose any number that's to the left of 0. I'll choose -1. For the interval in the middle between 0 and 1/2, I will choose, between 0 and 1, I will choose 1/2. And for the interval on the right from 1 to infinity, I will choose a positive 2. So now that I have a test value in each of those intervals, we have done step 2. We are going to plug these test values into the derivative not the original function. So what I want to know now is I want to know the sine of f prime. So I want to take the test value of -1 and plug it into the derivative. I'm plugging it in here. Comes out to be a +6, which is greater than 0. When I plug 1/2 into the derivative, we get out a -3/4, which is less than 0. And when we plug 2 into the derivative, we get out a +6, which is again greater than 0. So what does this tell us? Well, theorem 3.5 told us when the function is increasing and when the function is decreasing depending on the sign of the derivative. As for when the derivative is 0, remember, we found the only two places where the derivative was equal to 0. So now we're able to make a conclusion at the end of this table that where the derivative was positive and greater than 0, the function must have been increasing. Because theorem 3.5 tells us that if the derivative is greater than 0, then your function is increasing. And if the derivative is less than 0, like it was at 1/2, then the function must be decreasing. So we have determined on what intervals the function is increasing and what intervals it is decreasing. It's increasing on these two intervals and decreasing on the interval in the middle from 0 to 1. Now we define what it means for a function to be strictly monotonic. A function is strictly monotonic if it is always increasing or always decreasing. So for example, notice that as we move from the left to the right on the graph of x cubed, our pencil is always moving upward. So that function, x to the third, is strictly monotonic on its domain, on the entire number line, because it is always increasing. It would have also been strictly monotonic if it were -x to the third and would have always been decreasing. However, consider this piecewise function here. It goes from increasing to now it is constant between 0 and 1, and then it continues increasing. This is not strictly monotonic because it's not always increasing. It has that constant piece in the middle. So all strictly monotonic means is that the function is either always increasing or always decreasing. To talk about the first derivative test. To illustrate the first derivative test, let's go back and let's at this example here in example 1. In example 1, with this cubic function, we found that it changed from increasing to decreasing to increasing. Let's look at a graph of that. The graph is going from increasing to decreasing to increasing. And now let's look and see where this graph has relative extrema. It has a relative extrema here at 0, 0, a relative maximum where it changed from increasing to decreasing. And then it has a relative minimum where it changed from decreasing to increasing. The first derivative test states that this will always happen. It says, assume you have a critical number. And we did start off by finding 0 and 1 as critical numbers. And even looking at the graph, they're definitely critical numbers because the tangent line at 0 and the tangent line at 1 are horizontal, meaning that the derivative is equal to 0 because the derivative would have a slope. The tangent line would have a slope of 0 at those values. And so they're definitely critical numbers. So if you have critical numbers and you run through this process where you see this change in sign of the derivative, it goes from a positive derivative, hits a critical number, and then it changes to a negative derivative, that must mean that you have a relative maximum. Similarly, if it changes signs from a negative derivative, hits a critical value, and then switches to a positive, so it went from decreasing to increasing, that's what happened when it crossed over the critical value of 1, then that would mean that you have a relative minimum. So when we're using the first derivative test to show that we have relative extrema, we need to discuss how the sign of the first derivative is changing. Notice that if the sign of the first derivative does not change, if the graph goes from increasing to continuing to increase, there is no relative extrema there. Similarly, if the graph went from decreasing to continuing to decrease after crossing through a critical value, there is no relative extrema there. It's only when we see a change in sign from either negative to positive or positive to negative that would indicate that we have a relative extrema. Whether it's a maximum or a minimum depends on whether it went from negative to positive or from positive to negative. Now we look at example 2, where we will find the relative extrema of this function on this interval using the first derivative test. We begin by taking f prime. The derivative of 1/2 x is 1/2, and the derivative of sine x is cosine x. Now that we have the derivative, we go on and we look for critical values. In looking for critical values, we are looking for where the derivative is equal to 0 or where the derivative does not exist. So I will take the derivative and set it equal to 0 and solve this equation. I'm going to add cosine to both sides of this equation and get 1/2 is equal to cosine x. So we're looking for where cosine is 1/2. That will be pi over 3 and 5 pi over 3. So we have found two critical values. And for as where the derivative does not exist, this never happens because we know that cosine has a domain of all real numbers. So this derivative here will always exist. So now that we have our critical values, in order to determine whether or not we have relative extrema, we need to go and set up an interval. From 0, and I'm using 0 because this starts at 0, I definitely need to make sure that I have my critical values of pi over 3 and 5 pi over 3 on this number line. And then I will end the number line at 2 pi. Values give us intervals to consider. Remember that we are only working between 0 and 2 pi, and so our first interval is from 0 to pi over 3. Our second interval is from pi over 3 to 5 pi over 3. And our final interval is from 5 pi over 3 to 2 pi. And on each of these intervals, we will need to choose a test value. Interval, I will choose my test value to be pi over 4. That is a number that is between 0 and pi over 3. Then I need a number between pi over 3 and 5 pi over 3. I will choose pi. And then for a number between 5 pi over 3 and 2 pi, I will choose 7 pi over 4. Again, any number can be chosen here as long as it is between 5 pi over 3 and 2 pi. Now what we need from those numbers is we need the sign of f prime. So we're going to be taking these test values and we are going to be plugging them into the derivative. And when we take f prime of pi over 4, our answer is less than 0. When we take f prime of pi, when we plug pi into the derivative, our answer is greater than 0. And when we plug 7 pi over 4 into the derivative, our answer is less than 0. And I'm not going to use a final row here for conclusion because I'm not really looking for where the function is increasing or decreasing. I want to know where this has a relative extrema at. So what we're looking for, again, is we're looking for a change in sign of the derivative. So in our table, we can see that the derivative went from negative to positive as it crossed over the critical value of pi over 3. Going from negative to positive goes from decreasing to increasing implies that there is a relative minimum when x is equal to pi over 3. Look at the second critical value, we have to check again to see did the derivative change signs. Well, as we cross over 5 pi over 3, the derivative goes from positive to negative. which means the derivative went from increasing to decreasing. The function went from increasing to decreasing. That means that we have a relative maximum. So now we know the location of those relative extrema on this interval, as we can see illustrated by this graph here. Keep in mind, a relative minimum occurs when the derivative changes from negative to positive, which means that the function changed from decreasing to increasing. There is a relative maximum where the function changes from increasing to decreasing, meaning that the derivative went from positive to negative. When you are using the first derivative test, you have to show the sign of the derivative. To wrap this lesson up, we're going to look at one final example where we both determine the intervals of increasing and decreasing and use the first derivative test to find any local extrema. We have our function here. Do observe that 2 is not included in the domain of this function, and we begin by finding g prime. In order to find g prime, we are going to need to use the quotient rule. I will identify f as the numerator and g as the denominator. We will take f prime using the power rule, and we'll do the same with g. Now that we have everything we need, we are able to apply the quotient rule to find g prime of x. The quotient rule tells us we need f prime multiplied by g, and from that we subtract g prime being multiplied by f. I went ahead and distributed the negative in subtracting f. In the denominator, we have g squared. I will work on simplifying my numerator. And now that we have a simplified numerator, I will go ahead and look for my critical values. To find critical values, we are looking for where the derivative is equal to 0 or where the derivative does not exist. The derivative is a fraction, and fractions are equal to 0 when their numerator is equal to 0. Because we know that when the denominator of a fraction is equal to 0, then it would not exist. So when we're working with a fraction looking for critical values, we essentially set both the numerator and the denominator equal to 0, because where the numerator is equal to 0 will be where the entire fraction equals 0, and where the denominator is equal to 0 will be where the fraction does not exist. And now we will work on solving these two equations. This first quadratic equation can be solved by factoring. And the second equation, I will take the square root of both sides to get that x is equal to 2. Now we have maybe three critical values, but keep in mind with this x is equal to 2, that was not in the domain of the function. And so this is not a critical value because it's not in the domain. So our only critical values are 1 and 3. So now that we have our critical values, we are ready to go and make a number line and start testing values. On my number line, I definitely want to make sure that I put 1 and 3 on it, because this is going to split my number line up into intervals. The first of which will be the interval from negative infinity up to 1. We know that at 1, the derivative was equal to 0. Our second interval is between 1 and 3. We also know that at 3, the derivative is equal to 0. And our final interval will be from 3 till infinity. In each interval, we will need to choose a test value. In the first interval, the test value that I will choose will be any number that is less than 1. I will choose to use 0. In the second interval between 1 and 3, we can choose any number, but we could not choose 2. Okay, we could not choose 2 because 2 is not in the domain of the function. So instead, I'm going to choose 1.5. And then finally, any number bigger than 3, I will choose 4. So now that we have our test values, we want to take these test values and plug them into the derivative. And I need to fix this because our function is called g, not f. So this should be g prime, and this should be g prime, because our function was a g of x. So now we want to know the sign of g prime. So we're going to take 0 and plug it into the derivative. Plugging 0 in here would give us something that is positive. I'm then going to take 1.5 and plug it into the derivative, and that would give me something that was negative, less than 0. And when I plug 4 into the derivative, that would give me something that is greater than 0, positive. So now that we have these signs, we are able to make a conclusion about where the function is increasing and where the function is decreasing. From negative infinity to 1, a derivative greater than 0, a positive derivative, gives us an increasing interval. Between 1 and 3, a negative derivative gives us a decreasing interval. And from 3 to infinity, a positive derivative gives us an increasing interval. Now that we know the signs of the derivative, we are able to make conclusions about where we have a relative maximum and where we have a relative minimum, if any. Where the derivative changes from positive to negative, we will have a relative maximum. So we have a relative maximum at the critical value when x was equal to 1. I'm going to put the point 1, I'm going to go back and find this y value in a second, but I'm going to justify this. This is a relative maximum because g prime changed from positive to negative. Similarly, we have a relative minimum where the derivative changes from negative, decreasing, to positive, increasing, and that is when x is equal to 3. So we have a relative minimum at some point, and I know that because g prime changed from negative to positive. Now, let's discuss how to find what these y values are to give us this actual point. To get these points, I'm going to be plugging 1 and 3 into the original function respectively. Okay, so I'm actually interested in what was the y value on the function. So I'm going all the way back up here to get those values there. And when I plug 1 into the function g, we get out 2. And when we plug 3 in, we get out 6. So we can see that we have a relative maximum at the 0.12 and a relative minimum at the 0.36, which is confirmed by this graph.